This is Free Range Digital Design Foundation Modeling, Chapter 24. Issues in this chapter are things associated with clock. So we'll be working with setup and hold times, just some basic clock vernacular, and also we'll be exploring maximum clock frequencies in sequential circuits. Clock signals are extremely important in digital design. Most designs have some type of clock in them, and not all designs, but most meaningful designs. There is an area of digital design that's asynchronous digital design, which is a whole another science that we don't go into. But there's two types of clock signals out there. There's periodic clock signals and there's aperiodic. Periodic means the clock signal repeats itself after a given amount of time. So the given amount of time is the period. In this picture here, you can see that this periodic clock signal looks exactly the same the whole time, where this aperiodic one, we've got different looking signals in the high range and the low range. So anyway, nothing wrong with aperiodic signals, sometimes quite useful in many applications, but we'll be primarily working with periodic. So period is defined as the amount of time the signal requires to repeat itself, and here's an example of the period right here. We're looking at the two rising edges and the time it takes for one rising edge to appear and the next rising edge to appear. The period of the clock has reciprocal relationship to the frequency. Essentially 1 over the period is the frequency. Period is a time measurement and it has units of seconds. The frequency is not a time measurement, it's a reciprocal of the time measurement, which means it has units of seconds to the -1. Seconds to the -1 is kind of clunky. Everyone knows this as hertz. Essentially, we'll be working with hertz, and we'll be describing our signals as in gigahertz, megahertz, kilohertz, that type of thing. Now, the other issue here, the other quite common vernacular, is the notion of a duty cycle. Most clocks, you think they're high half the time, they're low half the time. Well, that's not always the case. Essentially, we can have clock signals that are periodic, where the high portion of the signal is different from the low portion. And here's an example here. And so the duty cycle is defined as the amount of time the signal is high over the period. So essentially it's a ratio that indicates what percentage of the time the signal is high. Because it's time over time, a duty cycle is a unitless measurement and quite useful. The duty cycle of a periodic waveform is often used to transfer information. So if the duty cycle is 10%, that means something, and that's different than a duty cycle of, say, 20%. It transfers information. Certainly the circuit that is using that signal can figure out that duty cycle and use that underlying information to do something important with. So here's an example. What we're looking for is the frequency of the waveform. What it's given is the duty cycle and the amount of time the signal is high. So we can go ahead and draw this. Not necessarily drawn to scale. This is 10 nanoseconds, and this the duty cycle. And what we're going to be looking for is this value right here. So this is the amount of time the signal is low during that period. So we can essentially just an algebraic equation here. So we got duty cycle, which is 0.25 equals 10 over 10 plus x. We'll drop the nanoseconds and remember that we're working with nanoseconds later. Uh, 30. And so, and then we'll add in the nanoseconds on the end of that. Nanosecond. Total period is 10 plus 30 nanoseconds. So the frequency is a period. So the frequency is 1 over period equals 1 over 40 nanoseconds, and we'll leave it in this form. That's good enough. Usually you might want to do the math on this and put it in hertz, but we won't go there. A super important item here is the setup and hold times of circuits. These devices, what we're working with, are physical circuits. We must obey the laws of physics. There's some important things that we truly must obey in the notion of synchronous circuits. If we don't obey them, the circuit doesn't work. This is a synchronous circuit. All the changes in the circuit are synchronized to that clock edge. Well, it turns out that I need to treat this D input here special, meaning I must hold it stable before this clock edge, and I must hold it stable after that clock edge. And so the notion here is the time I need to hold it stable before the clock edge is referred to as a setup time, and the time I need to hold it stable after the clock edge is referred to as a hold time. These are very important quantities. Generally speaking, in beginning digital design classes, we can often ignore that because our circuits are working at slow speeds. But in real life, if you violate the setup or hold time, as your circuit goes metastable, this is a common word you should know. Metastability means it's neither high or low, and it may stay there for a while, which essentially means your circuit's not going to work. I always tell the story that someday, probably not in this class, but someday if you're working with digital design and design your own circuit, and your circuit just won't work for some reason, and you just can't figure out why, you checked everything, you're suddenly going to realize, oh darn, I violated a setup or hold time, and you're going to correct it and your circuit's going to magically work. These are two circuits here. This is a rising edge here, and this is a falling edge. The setup and hold time is the same for each rising and falling edges, which means here's the active clock edge. I have to not change the inputs to the circuit on both sides of that clock edge, referred to as a setup and hold time. Now, we don't use setup and hold time much in this course, but one thing we will use it on is maximum clock frequency. So what we have here is a state machine, and it has a clock signal in there. It is a synchronous circuit, and the issue is how fast can I operate this circuit, meaning how fast can I get that clock cycle going and still guarantee the circuit is going to work. The issue is that at some point I'm going to violate setup or hold time, or some propagation delay is going to mess up the circuit. Can't keep increasing the clock cycle ad nauseum. At some point it's going to break, and so we're kind of interested in knowing what that point is. So in the big scheme of things, we have a couple circuits here. We've got these are both decoders, prop delays through them. This is a register sequential circuit. It has prop delays. It also has setup and hold time issue. We need to consider that in our circuit. The maximum clock frequency in a circuit, and we're consider just the simple state machine circuits, so what we're going to have here is we're going to have a setup time, we're going to have a propagation delay time through the flip-flop, and we're going to have a propagation delay time through the next state decoder. So we've set these problems up such that the output decoder is not going to matter. I mean, of course it matters in real life, but we want to keep these problems as simple as possible. And lastly, two other things here. We're going to put a safety margin in there. We're not going to design this to the edge of the spec here. We're going to put a little safety margin there typically. And lastly, what we do here is the propagation delay through the flip-flop is greater than the hold time. So that essentially simplifies the problem, makes it so we don't have to worry about hold times. We do have to worry about setup times, propagation delay times through the flip-flop and through the state registers, however you want to put it, and the prop delay through the next state decoder. Add those up, and that's going to give me a minimum period. I'm going to invert that, and that's going to give me the maximum frequency. So these problems are not really that complicated. Let's go ahead and do one. This is a problem very much like the last one. It gives me a bunch of times up there that I need to keep track of, and I want to know the maximum clock frequency in this one. I just call out a safety margin. It has a safety margin of 12 nanoseconds. So everything's in there. What I have to worry about is Tmin equals, this is the prop delay to the next state decoder. I've got a safety margin. I've got a setup time of the flip-flop, and then I have a prop delay through the flip-flop. So these are the four values I'm interested in. I'm going to sum those up here. So T min equals T next state, find this up here, 18 nanoseconds. The safety margin is 12 nanoseconds. The setup time, 10 nanoseconds. The prop delay to the flip-flop is 13 nanoseconds. Those are my four values. I'm going to add these up. So that's 30, 40, 53 nanoseconds. Tmin So then by the time I'm done here, frequency max equals 1/53 nanoseconds. And I'm going to leave it at that. Might want to do the math, put it in Hertz form, but this is good enough